Well, ladies and gentlemen, welcome to my today's presentation titled Case Study Integrated Approach to Sand Management and Completion Evaluation. My name is Muhammad Zahirin bin Ruslan, please call me Zach, and I would like to acknowledge CRISAP Subsurface as well as Well Services for their contribution to this project. Before I move any further, allow me to lay out to you my today's presentation. Firstly, I shall introduce to you where this project was developed. Secondly, I shall share with you what we would like to achieve with this project. Thirdly, I shall share with you what are the integrated methodologies that we have adopted for this particular well and project, followed by results evaluation, and last but not least, I shall open for question and answer session. Ladies and gentlemen, CRISAP is actually operated by Dong Oil and Gas, which is located in Denmark. The field or the asset is actually located approximately 220 kilometers offshore North Sea in the Danish sectors, and the average seawater depth is about 60 meters. The Siri Mother platform is actually an integrated processing facility where it actually comprises of the wellhead, the processors, as well as the accommodation. The three unmanned platforms nearby and subsea installations are all tied back to the main mother facilities. The processing facilities has not been really designed to handle significant amount of solid production. Thus, in alignment to that, most of the producers has been designed for downhole sand control as well as sand prevention. So, in the early around 2015, we started to face some challenges when it comes to solid productions. So the main challenges that we were facing, we can actually observe that the surface acoustic wellhead sand detector is indicating that we're having solid productions. And this is further confirmed by the amount of solids that we actually found when we do pigging on the flow lines, and as well as when we actually clean up the production separator. And additional to that, it has been quite a challenge for us to try to evaluate the condition or the mechanical condition of the screens downhole, especially in some of the long horizontal wells. So understanding of these challenges, capturing this, we decided to define the objective for this particular project, looking at to try to identify the root cause of the solid productions from well by well cases, and as well as to try to identify either new technology or set of technologies that we can actually utilize to actually evaluate the completion mechanical condition downhole, which is specifically looking at the screens condition. When it comes to Dong Energy as well as CRISAP, anything problems that relates to solid productions is being governed by the Integrated Sand Management System, the ISMS, which is actually comprises of 4 life phases, which are sand prediction, sand prevention, sand production, and last but not least, the evaluation and the feedback. And we have adopted as well one of the core tool in Lean Six Sigma, which is looking at define, measures, analyze, improve, as well as control. And throughout the time, we are actually as well emphasizing on continuous improvement and conserving the knowledge from well by well basis, because this is very valuable information throughout the history of the asset indeed. So from day-to-day operations, we have actually come up with high-level workflows. We're actually focusing on surveillance monitoring, as well as in order to safeguard the value of each well, as well as potentially looking at opportunities of well optimization. I'm not going to cover in detail these workflows, but what again I would like to emphasize is one of the critical factors in the success of these workflows, as well as the integrated sand management, is a great collaboration between multiple disciplinary as well as cross-segment, because this actually require a clear defined roles as well as responsibility. And then moving to looking at each one of the problematic wells, we start defining the fit to purpose, the integrated sand production evaluation. But in general, we actually separate that into 2 major groups, which are firstly looking at the surface sand management and analysis. We'll be covering looking at understanding the risk of the well in terms of solid productions, looking at the geomechanics model analysis. We start looking at how we have been operating the well, looking at the well operating envelope, what the opportunities that we can actually improve in order to manage the sand productions, try to minimize the risk. Then we start optimizing what is the best well surveillance monitoring for each of the individual wells. And of course, if we're able to actually collect some sample at the downhole or at surface, we have sets of standard evaluations in order to gain a better understanding the source of the solids. And the second part, we'll be looking at the downhole completion analysis. So this is an example of workflows that I will walk through during the case studies discussion. But prior defining this, we have developed all the cases we're looking at, try to understand what is the well conditions, as well looking at defining what is the decision tree for each of the cases, which is incorporate the risk and gain elements, as well as then we went through two sets of peer reviews to ensure that all the workflows or the work scope that we're going to intervene into the well is optimized in terms of probability success, how we can actually succeed, and as well as for contingency planning. So by combining all these multidisciplinary evaluations and results, it's actually enable us to identify what is the most technical as well as economical solution. For example, in this particular case, we could potentially look at evaluating the sense on fines prevention. We could be looking at, do we actually need a downhole remedial sand control, or even as simple, relatively simple, of handling the solid production at surface in terms of looking at sand management. Let's proceed into the case studies. So as we started entering the well, we started with performing the drift run. We will actually recover small amount of metal rasping and small amount of wax. So we've sent this metal rasping for composition analysis to actually understand what's the origin. So if you're looking at the compositions in terms of molybdenum, nickel, magnesium, and chromium, it's actually match the production tubing composition, which is a super 13 chrome. So, and then we start looking back a little bit on the historical of, and the caliper that we performed historically. We can actually see some minor groove, very small, and then potentially we might not see it that clear because we know that in this particular well, it might be slightly coated by scale, and most of the time it has a wax deposit. So internal discussion, we actually believe that one of the root cause of this metal rasping is basically due to the multiple wax cutting jobs that we have actually performed in this well, down to an average about 300 meter measured depth. So that could be one of the major causes, because all the tools that we actually pull out, we actually check that the tools were in good conditions, and this confirmed by the composition as well. It comes from the production tubing itself. And then we proceed into the well, and fortunately we didn't actually encounter any restriction, anything less than 500 meters, which means that we did not have a significant wax deposit in the tubing, so it's a good thing. And then we start structuring further down and performing with wireline sand bailing. And when we reach this depth, about 2,450, we actually encounter a solid tag. So we tried multiple times, so we were unable to actually tractor deep into the well. And during few of the runs, we only recover a relatively small amount of solids. So something is just not right there, because if it's something that has been totally filled, that we anticipate that we will recover more solids, but we only have very small amount of solids recovered in the sample bailer. So in order to understand what is actually problems, we decided to perform, to run the imprint block LIB. So this is a condition prior running, and upon pull out of hole, we can actually only some minor dent, which is what we anticipate to see, especially in the horizontal wells, where the side pocket mandrel is highly deviated of the part of the well. But on the face of the imprint, we didn't actually see any idea what is causing the blockage. So the internal discussion again, and we decided we do need to run the caliper. So we decided to run a caliper run. So we managed to get a fast turnaround results, and when we actually correlate the BHA depth with the results of the caliper, we can actually observe that the first wheel of the tractor is actually within the profile of the formation isolation valve. And then when we zoom in that particular depth, you can actually clearly see the profile of the isolation valve. So basically the sealing sleeve did not actually went down to protect the flapper, and then the first tractor wheel actually was stuck in the profile. So discussing with the providers, and then we decided to actually run 2 tractors in tandem. So basically, as we tractor down, as the first tractor reached the profile, we deactivate that and start tracting with the second tractor, and moving forward. And then once the second tractor reached the profile, we start tractoring with the first tractor again, and we're able to reach TD without any problem. And of course, that was one of the surprises that we seen. We didn't anticipate that it was the flapper is actually still not covered. So looking at the caliper results, as we actually perform it into the sand screen sections, we know that looking at the results, we can observe that the pre-perforated base pipe is as per specification. They are in relatively good condition. So this is a good news. But at this particular time, we know that the base pipe is good, but we have no idea what is the condition of the melter mesh outside of this base pipe. But in general, we can say as well, there's slightly coated with some scale of deposit as anticipated. But at the end, close to TD, we have slight oval features, but it's nothing that we're so concerned about. And then we continue to do caliper on the upper completions on the way pulling out. We're able to identify the main components in the well. Generally, it's in good condition. This is what I anticipate because the methodology is optimized for the flowing conditions of the well. It's super 13 chrome. The maximum pitting we found is about 18.09%, and the maximum civet meter loss is about 4.33%, yet it's actually below the API tolerance. So that's a good news, and that's what we actually anticipate. And then we further going for the next programs of logging, we actually went through for electromagnetic survey, where we'll be looking at evaluating the screen conditions. We'll be looking at to actually confirm the tubing conditions if there is any deposits. So we try to actually evaluate the actual tubing conditions, as well as through tubing to evaluate the casing. For the electromagnetic survey, so this logging tool is actually functioned on the base of remote field eddy current. So basically, the transmitter, it has 12 sensors actually mounted on the collapsible spring bows, and then it actually transmit electromagnetic field, and then the receiver will be measuring what's the response, what is the amplitude and the frequency. So evaluating on that, it gives us an idea of the thickness of the metal at that particular depth that we were logging. So proceed with the sunscreen evaluation. So prior to the actual intervention, we have performed the logging into few good joints of the screens in the yard, and then we actually measures the fingerprint, what is the response for a good joint. And then when we actually perform the actual logging, which is, for example, this is a particular one. So we're looking at this particular joint, we were looking at what's the responder phase as well as the amplitude. We can actually see the difference response in the actual measurement. So this is actually an indication of potential damage of the screen's downhole. So the base pipe is good, we didn't see any problems, but we actually found in about 4 joints of the screens that we have potential compromise or potential damage. Looking at which sensors actually recorded that, as well as the length that was recorded, we somehow can able to estimate what is the potential size or the which sides of the damage that we could potentially looking at. So, but then of course it's not relatively direct measurement, so that's why I still emphasize on the use potential. So in order to actually gain more confidence on that, I will combine that with the different sets of evaluation. So, and to summarize the results of the electromagnetic thickness evaluations, so we continue to logs on the tubing. So the tubing in alignment with the caliper results is actually in good conditions. In the measurements that we actually see the results is looking at about 6.5% metal loss, which is slightly higher than the caliper. But remember that when you actually using caliper to actually evaluate the tubing condition, if you have any scale or deposit, then you're not going to see the actual correct ID of the tubing. So whereas the electromagnetic, you will actually bypass that. So, but then again, 6.5% less than the API tolerance. So it's not concern for us. So that's a good thing. And then we perform the casing evaluation, which is through tubing. So we actually run into the tubing and evaluate the casing behind that. And it shows that the casing in a good condition. This is as well what we anticipate because we have a good corrosion inhibition program for the gasket that we inject through. And it's still less than 12.5% compared to the API tolerance, so a good thing. And then recap on the sunscreen. Generally, it is a good condition. Only 4 joints that we believe there's a potential compromise condition as indicated in the response in the previous slide. So we managed, remember that I mentioned that we managed to get a small amount of solids from the sand baling, and we managed to actually recover some solid as well at the test separator. So we sent both samples for particle size distribution. So in this particular well, the screen, the premium screen has an opening about 175 microns. So approximately 20% of the recovered sample, solid downhole, as well as at the separator, 20% of that actually bigger than 175 micron. So that gives us an indication that yes, we do have some screen that has been compromised. And then, but then 80% of that is actually below the screen opening. So that further highlight to us that in order to handle that, we do need to look at how we can actually optimize the well operating envelope in order to actually manage and minimize the amount of potential solids that will able to pass through the screen opening and being produced to surface. Additionally, we perform in the same intervention period a production logging to basically try to say where is the potential damage corresponds to the inflows and is there any risk of hotspots. Fortunately, most of the productions does come from the toe, and some of the areas does as well corresponds to where we actually saw the damage, and it does indicate certain risk of hotspots into the screen. So as at this particular time, you have seen that we have combined multiple evaluations, multiple log, and multiple analysis from either surface as well as downhole to try to understand the condition of the well. So allow me to summarize a little bit. So we can actually see that the screen relatively in good condition. The base pipe of the screen is good. The screen relatively in good conditions. There's about 4 minor potential damage joints as identified by the electromagnetic logging. And then the downhole samples indicate 20% of it is actually bigger than screen opening, which is further confirmed we do have screen damage downhole. The production logging does indicate there's a risk and potential of hotspots and damage to the sand screen. Tubing, but on the good side, tubing is good condition, casing is in good condition. So by compiling and understanding all of what actually risk we have in the well, what the actual condition of the well, it helps us actually to identify what is the best way forward. Remember earlier we were considering, do we need to do sand prevention, the fines prevention, do we actually need downhole remedial or not, do we need actually surface management, do we need surface descender to actually handle this because the facilities are not meant to handle significant amount of solid. So, but then now we are well informed with a more reliable data to make optimized decisions. We decided to go for sand prevention. Firstly, we actually producing the well to the minimum flowing bottom hole pressure that we define, which is translate that to production rate exclusions, as well as we has optimize the well operating envelopes to actually minimize the slugging to ensure that the well is producing as stable as possible. This is as well based on that 80% of the solid that we recovered is actually smaller than the screen opening. So these two has been all in place, and we're looking at from 2015 until now by optimizing the well operating envelope, by defining what is the well flowing conditions. We can actually see is that the sanding trend has actually reduced. So I'll walk through a little bit on this graph. So as you can see on this axis is the sand production volumes on monthly cumulative. So that is actually the green line, the line graph in green. You can see that we started with relatively high, and now we actually almost a very small amount. And then this is the monthly cumulative liquid volumes, and then that is the number of startups. So most of the time, at what period we actually observe that the well is actually producing more solid, because we have the surface sun detectors, is that the pond startup, or when the well is slugging, that is the most time where we actually see the solid being produced. So we put an extra focus on try to identify what is the best condition, what the flowing condition to actually to have a soft startup, and as well as try to reach a stable flowing condition as fast as possible to minimize the potential amount of solids being produced to surface. And of course, this is one of the main key factors in success of try to operate startup this well is a strong collaborations between the onshore team as well as the offshore team and the multiple disciplinary approach of this. So moving to the conclusion, I would like to emphasize again the integration of multiple downhole and surface evaluations is actually helps us to really identify what is the downhole screens conditions as well as the condition of the tubing and casing. As well, that actually helps us to see, is our corrosion inhibition plan is good? Do we need to do something to control it before it goes too late? And secondly, integrated and multidiscipline evaluations based on reliable acquired data actually helps us to optimize the decisions, the way forward, short, medium, and long term, to actually fit for purpose for well by well basis. And remember, this is a mature field, relatively mature wells, so they do need an extra attention and care. So I would like to acknowledge Dong Energy and DEA for allowing me to actually share today's case studies. And now I shall open for question and answer session.